One of the best regression models that I had ever seen had a R-square of 0.96, and yet it became one of the most expensive ones for the company who created it. A pharmaceutical quality director built that model for an FDA audit. She used 18 months of data and hundreds of batches. Statistically, the model looked perfect, and the audit was approved with no findings at all. However, when we reviewed the documentation, I noticed something strange. The diagnostics folder had only one page with the R-square value. I asked the uncomfortable question, where are the residual plots? She answered, the statistician we hired said that with an R-square like that, they are not needed. 3 months later, one 2.3 million batch was rejected. Quick pause. R-square is the measure between 0 and 1 that shows how much of the variation in your data model it is explained. An R-square of 0.96 means that the model explains 96% of what is happening in the real world. It sounds perfect, and that's the real problem. Using regression without checking the residuals, which are simply the difference between what the model predicted and what really happened, is like a doctor running advanced tests but never taking your temperature or blood pressure. R-square is the expensive test that looks impressive. Residuals are the vital signs. And a patient with an unstable vital sign is in danger, even if the advanced test is looking perfect.
Welcome to Advanced Quality Programs with Juan Navarro. In this podcast, we're going to dive deep into the world of quality and leadership philosophies.
Today, I'm not going to give you formulas or manuals. I'm going to give you tools for your judgment. The ability to look at models the way a doctor looks at a patient, not only at the impressive test result, but also at the vital signs that show whether everything is really working or not. Now, coming to the start point, a regression model. In simple terms, that is a tool for understanding which variables affect your results. Instead of guessing, the model will tell you if you raise the temperature by 1 degree, your defects will go down by X units. But this is only working if the model is built correctly. When I started working, I treated regressions like an advanced calculator. I entered variables that looked at coefficients and celebrated these R-squares. Then one of my own models with a R-square of 0.89 recommended changing the temperature on an assembly line. The result was 40 hours of unplanned downtime and me working late at night. The model was significant, but the residuals formed an arc and I did not even check them. Imagine you are a commercial pilot. You have 200 passengers. Your plane is a Boeing 787, a state-of-the-art aircraft, but before takeoff, what do? You use a checklist. It is the same idea since 1935. When an accident showed that even the best pilots can forget critical steps, if they only rely on memory, it is incorrect. It does not matter how many hours you have or how advanced the plane is. Without a checklist, nobody takes off since that time. Regression is the same. The plane is your model. The pre-flight check is made up of 6 checks, and if you skip them, you are not taking off without knowing whether your instruments are working or not. So let's go through those checks. Check 1. Does the relationship make sense? And that's just checking the data in pure logic. Let's say if ice cream or ice cream sales predict drownings at the beach, that is not an useful model. It is a coincidence. For example, heat could be a real cause. If the relationships does not make sense, you do not take off. Now check 2. Is the relationship straight or curved? Forcing a curve into a straight line is like using a speedometer that only goes up to 80, and when you are driving at 180, you don't even notice. If your data is curved, you need to transform it. Now check 3. Are there extreme values that distort everything? If most of your time are 2 minutes, but you are 4 hours, those huge 4 hours values can pull the whole model in the wrong direction. Understand why is that happening. A logarithmic transformation can help because it compresses a large value so that they do not dominate the complete scale. Now check 4. Are there unusual data points or errors? One bad data point can tilt your whole line like gust of crosswind. Review those points. If there are errors, remove them. Do not ignore them, analyze them. And do not ignore them simply because they are inconvenient. Now check 5. Do the variables move together? And let's say that the open temperature or the warehouse humidity change at the same time. The model does not which one is causing the effect. This is called multicollinearity. I call it confusion. Now check 6. Is the distribution reasonably balanced? If it's not, the residuals will make you pay for it. Residuals are like gravity. You can ignore them, but they are still there. Let's go back to the pharmaceutical director. Her data was really good, but when they checked the multicollinearity, we saw that the temperature and the mixing speed had a real correlation, one of 0.91. They moved together almost all the time. The model gave all the weight to the temperature, while the real problem, speed, was still hidden. Then we checked the residuals and found some repeating patterns. The model worked well and right from the beginning, but after the reactor maintenance, they failed right before the maintenance. The R square of 96 hit that pattern, and that 2.3 million batch failed right before that maintenance. The model did not see that because nobody did the pre-flight check. Now, I'll give you the pre-flight rule for the next time. Rule 1, 90% of the work happens before you run any model. Explore your data the way the pilot checks the aircraft. The 6 checks are not optional. They are what separate a safe landing from an accident. The rule 2 is residuals do not lie. If they look like a funnel, meaning the spread grows at high values, or if they form an arc or follow repeating patterns, your model is wrong, no matter how high your R square is. Rule 3. A high R square does not mean the model is healthy. You can have a patient with a perfect lab result, an internal bleeding that those tests did not detect. Statistical significant, the stamp that says this is probably not random, is not the same as practical impatience and importance. And when you use categorical values, such as working shifts, supplier types, remember these all options in the same category stay together or go together. Never remove them just at once. Edward Deming said, without data, you are just another person with an opinion. I would add this, with poorly explained data, you are just another person with an opinion and nice looking charts. Think about your last project where you used regression. How many of the 6 checks did you make before presenting your results? If you did fewer than 4, your model took off without a pre-flight. And that's it for this week. Thank you all for your reviews, of my books, The Quality Mindset, Principles of Quality, and Life Quality Projects. If this episode gave you a checklist you didn't have, please hit like, subscribe, and share it with a colleague who still flies without instruments. Stay excellent, keep improving, and do your pre-flights.
One small change triggers everything. Watch how agile thinking works. Inspect, adapt, repeat. Each step builds the next, creating confident, unstoppable momentum. This is The Quality Mindset by Juan Navarro. Get your copy now.